What is super cola? Hello, engineering enthusiasts. Have you ever stopped to think about how a product as small as a tube of superglue can bond materials with such impressive strength, even withstanding intense mechanical stress? That instant substance that fixes everything from a broken vase to delicate electronic components. Behind this seemingly simple efficiency, there's an accidental story, scientific discoveries, and fascinating chemistry. But first, what exactly defines superglue? Basically, superglue belongs to the cyanoacrylate family, adhesives that rapidly polymerize when in contact with moisture, forming extremely strong bonds. This ability to create almost instant bonds has revolutionized everything from home repairs to medical and industrial applications. But to reach this point, it took an unexpected journey of research and laboratory accidents. But how did this invention come about? The story of superglue begins in 1942 during World War II, when Dr. Harry Coover and his team at Eastman Kodak were investigating materials for precision weapon sights. During experiments with cyanoacrylates, they noticed an inconvenient property where the samples stuck irreversibly to everything they touched. Frustrated by the useless characteristic, the project was shelved. 8 years later, in 1951, while researching heat-resistant polymers for military jets, the same Dr. Coover came across cyanoacrylates again. This time, the researcher Fred Joyner demonstrated the adhesive potential by joining two refractometer prisms with a drop of the substance, and tests confirmed extraordinary adhesion on various materials. After years of development, in 1958, Eastman 910 hit the market as the first commercial instant adhesive. The name superglue became popular when the product was demonstrated on television in 1959, suspending a studio technician just by the soles of his shoes glued to a beam. But how does this instant adhesion work? The magic lies in the chemical reaction triggered by water molecules. Cyanoacrylates are monomers that remain stable in dry environments, but they polymerize violently when they come into contact with traces of moisture, including those present on the surface of most metals or in the air. When applied, the hydroxyl ions from water initiate a chain reaction where cyanoacrylate molecules bond to each other, forming long polymer chains in seconds. This exothermic process generates noticeable heat and creates a dense network that fills micro irregularities on the surface. Interestingly, the effectiveness varies according to relative humidity. Below 40%, curing may fail, and above 60%, it accelerates exponentially. The final strength arises when the polymer chains interlock mechanically and establish dipole-dipole bonds with the substrates. But what types of superglue are there? Although superglue is often associated with ethyl cyanoacrylate, which is the most common, variations in the chemical structure result in distinct properties. Methyl cyanoacrylate offers greater rigidity and thermal resistance but less flexibility. For industrial applications, ethoxyethyl cyanoacrylate provides less skin irritation and better performance on difficult plastics, such as polyethylene. In the tough or strong versions, synthetic rubber additives provide resistance to impacts and vibrations, making them ideal for automotive parts. In humid environments or on passivated metals, formulations with special accelerators ensure immediate curing. Even in medicine, butyl cyanoacrylate has been used since the 1970s to close surgical incisions and wounds, replacing traditional sutures. Recently, low cytotoxicity octyl cyanoacrylates have become the standard in dermatological adhesives. But how are they produced industrially? The manufacturing follows a synthesis in two main steps. First, ethyl cyanoacetate reacts with formaldehyde in an alkaline medium, forming a prepolymer. This material then undergoes pyrolysis to regenerate the pure monomer. The resulting liquid is distilled under vacuum to remove impurities and stabilized with additives such as sulfur dioxide to prevent premature polymerization. In the filling line, thickeners, accelerators, and pigments are incorporated. The process requires strict control of temperature and humidity, where any trace of water triggers irreversible solidification in the equipment. Although the basic formula seems simple, manufacturers have kept the exact compositions as industrial secrets for decades. And what are the applications of superglue besides the obvious ones? Versatility has turned superglue into a multi-sector tool. In forensic medicine, cyanoacrylate vapors reveal fingerprints on non-porous surfaces where the polymer crystallizes over fatty acid residues, making them visible. In civil construction, high-viscosity versions are used to repair cracks in concrete. The aerospace industry uses modified formulations for fastening components in satellites where they withstand extreme vibrations and vacuum. Restoration artists apply microdrops to consolidate fragile sculptures. Even in dentistry, cyanoacrylate temporarily seals crowns on our teeth. In everyday life, its usefulness extends to emergency repairs, from shoe soles to broken smartphone cases. Superglue was discovered by accident, but the major engineering projects that use this technology on a large scale are anything but improvised. In oil platforms, refineries, and industrial facilities, every adhesive, every fastening, every decision requires a skilled and responsible engineer. But getting back to the topic, what precautions does this superglue require? Its use requires attention. Contact with skin causes immediate adhesion, and it's estimated that 5% of users have accidentally glued their fingers together. Baths in pure acetone dissolve the bond, but they pose dermatological risks. Adequate ventilation is recommended because the vapors can irritate the eyes and respiratory mucous membranes. On porous substrates, such as wood or leather, white stains or blooming appear due to the reaction of the volatile monomer with residual moisture. To avoid brittleness, do not apply it to joints that are subject to constant flexing. Interestingly, storing it in the refrigerator extends its shelf life, while heat speeds up degradation. Wait, but for me, this thing about keeping it in the fridge was a myth, so is there some truth to it? Storing superglue in the refrigerator between 5 and 10 degrees Celsius. It's a valid practice and even recommended by manufacturers like Loctite in technical manuals, because it significantly reduces the rate of hydrolysis, which is a chemical reaction between the cyanoacrylate monomer and traces of moisture in the tube. The cold slows down the rate of this spontaneous degradation, extending the shelf life by up to 3 times compared to room temperature. However, it's essential to let the bottle reach room temperature before use. That's because cooling increases the viscosity of the liquid, making application and water condensation more difficult. When opening the tube, premature polymerization may begin. In addition, repeated cycles of heating and cooling accelerate degradation, making this method more effective for sealed and rarely used packages. Therefore, it's not a myth, but it does require operational care to avoid adverse effects. But is technology still advancing? Research is focused on overcoming historical limitations. New photo indicators allow curing under specific ultraviolet light, giving time for repositioning before fixation. Hybrid compounds with silanes increase adhesion on glass and ceramics. In bioengineering, biodegradable cyanoacrylates are being tested for temporary implants. Companies like Loctite have developed gels with adjustable curing times ranging from 5 to 90 seconds for complex assemblies. In 2021, researchers from the Massachusetts Institute of Technology announced a derivative that detaches on thermal command, making it easier to recycle electronic components. These advances ensure that even after 70 years, this accidental glue continues to reinvent itself as a pillar of innovation in adhesives. If you've made it this far and enjoyed the video, take the opportunity to subscribe if you haven't already, leave your like and activate the notification bell. And if you find our content interesting, consider helping us so we can keep producing content here on the platform and be remembered in our videos. So, do you have super glue at home? Do you keep your super glue in the fridge? Have you ever glued your fingers together? Leave it here in the comments, I want to know. Right here on the side, there are two interesting video options that you need to watch to expand your knowledge and explore your curiosity. And if you want to support us, leave your like, subscribe to the channel, turn on the notification bell, and consider becoming a channel member. That's all, engineering lovers. Big hug. See you in the next video.